This lesson is for section 2.5 on the chain rule. Today our objective is to use the chain rule to find the derivative of a composite function. So let's begin with a brief review of composite functions. In our first example, we want to find f of h of x when h of x is defined as 4x squared and x cubed is f of x. So in order to find this composite function, we want to take f and use h of x, which is 4x squared, and input that into our function f. So this becomes now the input for f of x. So we have 4x squared to the third power, and that ends up being 64x to the sixth. Now in our next example, if we want to find f of g of h of x, we're going to take h of x and use that in the input of g. So we would want to find f of g of 4x squared, and if I input 4x squared into g, I have f of cosine of 4x squared. Now that becomes the input now for f. So now I plug that into the function f. So this is the new input here. So we have cosine of 4x squared cubed. Okay, and you can write that also as cosine cubed of 4x squared. So you could write that either way here. Now for g of h of f of x is now the input for h. So if we want to find this composite function, we need to take g of h of x cubed. So first we're going to work on taking x cubed and making that the input for h. So we have g of h of x is 4x squared, so we need to take 4 and then multiply that by x cubed squared. Okay, this is the input now for g. Let me just simplify that. So that becomes 4x to the sixth. And if we take g and input 4x to the sixth, here we end up with the cosine of 4x to the sixth. So this here is that composite function g of h of f of x. All right, in example 2, we are told that some composite function f of g of h of x is equal to the square root of the sine of 3x. Now, based off of this particular function, we are supposed to determine f of x, g of x, and h of x. So right away, I noticed that 3x, which is a function in itself, is actually the input for this sine function. Now, the sine of 3x is the input for this square root function. So if we wanted to break this down, we would go from the innermost, work our way outward. So h of x here, the innermost function here, has to be 3x. Now for g of x, we're inputting h of x here into this sine function, so g of x must be the sine of x. Now, finally, we would take sine of 3x and input that into the square root function, so f of x must be the square root of x. So this is a really important skill here for being able to take the derivative of composite functions. You need to make sure you understand how to work your way from the inside out, but specifically when we use the chain rule, we actually work our way from the outside inward. So we need something called the chain rule in order to differentiate composite functions. Now in our previous lesson, I gave you guys a trig function that was actually a composite function. I gave you the function y is equal to the sine of 2x. And what we had to do in order to differentiate this was to first rewrite that, because we didn't know the chain rule at the time. We had to rewrite this using a double angle identity as 2 times the sine of x times the cosine of x. Now, once we rewrote this as a product, we then used the product rule, and we found that the derivative was 2 times the cosine of 2x. Now, that actually took us quite a bit of work to find that derivative, and on something like this next example here, if you had to find the derivative first by multiplying out every single one of these terms, that would be insane, right? So this chain rule is very powerful because it allows us to take the derivative of composite functions much more efficiently and very quickly. So what the chain rule states is that if you have some composite function here, y is equal to f of g of x, and you let y equal f of u, and u equal g of x, and you can see that if you just plug that back in, you'll end up with f of g of x, then what you're going to do to find that derivative of this composite function is you're going to find dy du and du dx. So provided that they both exist, then the derivative of y with respect to x is defined as dy du multiplied by du dx. In other words, we find the derivative of y with respect to u, and we multiply that by the derivative of u with respect to x. So we differentiate both of these separate functions here, and then we end up with the derivative of that composite function. Now I want to mention one thing about this notation here. Sometimes when students see this, they think, oh yeah, du and this du here, those cancel, right? Because those are common factors, and then that of course would leave you with dy dx. But this is really not what's happening algebraically at all. Du dx does not mean du divided by dx. This is one entity in itself. So dy du and du dx, these are separate ideas. They don't factor and cancel, although it is kind of a helpful way to remember, to find dy dx. You take dy du and multiply that by du dx, but it does not algebraically like cancel and factor, okay? Now, for the rest of this notation here, I'm going to break this down as well. I think it's intimidating at first. Once we start doing some actual problems, you're going to be like, oh, the chain rule is super easy. But right now, just to kind of get through the notation here, I think is tough. So f prime of u is really just dy du. Remember, we let y equal f of u, so that's just dy du. And this portion here, g prime of x, that's really just the derivative of u with respect to x, because we defined u as g of x. Now, to the right of this statement here is just the same as the one here. Okay, we're just making the substitution back in that u is equal to g of x. So it's mathematically equivalent. Oh, I forgot parentheses around this x, sorry. So these are just mathematically equivalent. So what we're saying is that this statement here is equivalent to the statement to the left, which is equivalent to this statement, which finds the derivative of y with respect to x. So this is what we're going to focus on. We are going to be taking the derivative of a composite function by using this piece here. So all that this states is that if you're finding the derivative of that composite function, you're going to take the derivative of the outside function with respect to whatever's on the inside, and then multiply that by the derivative of the inside function. So if we go back to that original example, y is equal to the sine of 2x, and we want to find the derivative of y with respect to x by using the chain rule. Here what we can do is assign u to equal 2x, right? Now we're looking at y is equal to the sine of u. So by the chain rule, what we're able to do is take the derivative of y with respect to u first. So dy du. Then we can multiply that by the derivative of u with respect to x. So du dx. So just by looking at the two pieces here, the sine of u, that derivative, would be the cosine of u. Then we multiply that by du dx. The derivative of u with respect to x is simply 2. Now if we make the substitution back in here, u is equal to 2x, right? We define u to be 2x, so that's just cosine of 2x multiplied by 2, or 2 times the cosine of 2x. So our derivative, y prime, is 2 cosine 2x, which is exactly what we got here when we used the product rule. Alright, so you're probably thinking that finding the derivative using that chain rule wasn't very quick at all, and I agree. Because we used all this notation here and we kind of broke it down using that whole definition, it did take quite a bit longer. What we're going to do, let me erase here, is we're going to focus, like I said, on this particular definition, this portion of the definition. So if we take a look at our first example here, we want to find the derivative of y with respect to x. Now, whenever you're working with the chain rule, you work your way from the outside inward. In other words, you're kind of peeling back like an onion. You want to work on your outer layers and work your way in. So in this particular function, I'm looking at a function that's raised to the 19th power. Okay, this is your inside function, and it's raised to the 19th power. Now, to differentiate this, we're going to bring down that 19. We keep the inside the same, 7x squared plus root x, and raise that to the 18th power. Right now, all we've done is found this portion here of the derivative. Okay, now by the chain rule it says now you have to multiply that by the derivative of the inside function. So this is your inside function here. If we multiply that by the derivative of this, that would become 14x plus 1/2 times x to the negative 1/2. So it's not a very pretty looking product here, but that is the derivative of y with respect to x. Alright, now in example 2, we are given the function the tangent of 7x squared, and we're asked to differentiate this with respect to x. So when we use the chain rule, remember you have to look at the outermost function first. You're peeling back the onion, so you look at your outer layer. Now this is primarily a tangent function, okay? This is what we evaluate the tangent function with. We input 7x squared into the tangent of x, but this is primarily a tangent function. So when you differentiate this, you're going to first take the derivative of the tangent of something. So that derivative is secant squared. Okay, so when I say the derivative of tangent of something, it's because we just put 7x squared, whatever that something is, we keep it inside. Then by the chain rule, we have to multiply it by the derivative of that something, the inside function. So we're going to multiply that by 14x. So the derivative with respect to x is 14x multiplied by secant squared of 7x squared. Okay, now sometimes you should try to simplify, but this is as simplified as this particular function would get. All right, in example 3, we're finding the equation of the tangent line to the graph of this composite function here, the square root of x squared plus 4 at the point where x is equal to 0. So here we're just weaving in some old skills. If we want to find the equation of the tangent line, we need to find the slope of that tangent line by finding the derivative. So we'll find y prime. Now, in this particular case, we're looking at a composite function where the outer layer here is really a square root function. So x squared plus 4 is the function we input into the square root of x. So we first need to differentiate this function as if it were just a square root function. So we take 1/2 and multiply that by x squared plus 4 to the negative 1/2 power. So this is just differentiating the square root function. Now we multiply that by the derivative of the inside function, x squared plus 4. So we get 2x. So if we just kind of put this together, we have, as it's simplified, those 2's would cancel here. So we have x over the square root of x squared plus 4. Now if we are looking for the equation of the tangent line when x is equal to 0, we have to plug in x is 0 into our derivative here to find the actual slope. Now when you do that, you end up with 0 divided by the square root of 4. So this is not undefined, it's actually just 0. So that's telling you that the slope of this line is 0, so you have a horizontal tangent. Now what we need to do is figure out the actual xy coordinates, okay? Because right now we don't know exactly where it's intersecting, we just know that the x value is 0, so we'd have to plug that into our function here to find y. So y in this case is equal to the square root of 4, or 2. So we're looking at the equation here, y is equal to 2. That is that horizontal tangent. All right, now moving on to example 4, we are given two different functions, f of x and g of x, and we are supposed to find the derivative of the product of f of x and g of x. So in other words, let me define y to be 3x plus 5 to the 7th power multiplied by the tangent of 10x. Now, we are finding the derivative of a product, right? So we still have to apply those same rules that we used before. It's just that each of these terms is now in itself a composite function. So we have to combine all of these things, the chain rule and the product rule here. So the derivative of y with respect to x, if we are just using our product rule here, would be f times g prime plus g times f prime. Okay, so that's what we'll have to work on. The first thing we want to do is just take 3x plus 5 raised to the 7th power, and then we'll multiply that by the derivative of the tangent of x. So remember, when you take this derivative, you're taking the tangent of something and finding that derivative. That will give you secant squared of that something, so secant squared of 10x. Then we differentiate the inside, so that's just 10. Okay, so this is our first part, f times g prime. Now we're going to add to that g, which is the tangent of 10x, and multiply that by the derivative of f of x. So again, it's now a another composite function. So to take this derivative, we need to multiply 7 by 3x plus 5 raised to the 6th power, and then we'll multiply that by the derivative of the inside, which is simply 3. Now there's not a whole lot of simplifying that can be done here. Let's write this as 10 times 3x plus 5 to the 7th multiplied by the secant squared of 10x plus 21 times 3x plus 5 to the 6th, 3x plus 5 to the 6th multiplied by the tangent of 10x. Okay, so this is that derivative with respect to x. Okay, in example 5, it says a particle moves along the x-axis so that its position is given by this particular position function, and we want to find the velocity, which really means the instantaneous velocity of the particle when time is equal to pi over 3. So to find this velocity, we're going to take the derivative of s with respect to t, because that'll give us our velocity function. Now I'm just going to rewrite s of t a little bit differently. Instead of writing it as sine squared, I'm going to write that as the sine of 3t squared. Okay, now when we take the derivative, the outermost function here is really something squared. So to take that derivative, we first work on differentiating something squared. So we have 2 times the sine of 3t raised to the 1st power. Okay, now we work on taking the derivative of the inside term. Now the derivative here, okay, this is another composite function. This is now primarily a sine function, so the derivative of sine is cosine. So we have the cosine of 3t, then we must multiply it by the inside derivative. of 3t. So that derivative here is 3. So we end up with our position function here, which is really the velocity function. That's equal to 6 times the sine of 3t times the cosine of 3t. So at this point, we should be evaluating the velocity function here when time is pi over 3, right? So we could plug that right into here and then evaluate and find the slope of that tangent. However, I'm going to come back here and actually look at this portion here. You might have recognized this as a double angle identity. That would just be the sine of 6t, right? So this is really 3 times the sine of 6t. It's a little bit easier than evaluating this. So we're looking at 3 times the sine of 6 times pi over 3, which is 3 times the sine of 2 pi. So here we end up with just 0. Now in example 6, we are given two different functions. We have y as a function of x and x as a function of t. We're going to find first dy dx and dx dt. Then we'll use those results to find dy dt. In other words, to differentiate y with respect to t. So the derivative of y with respect to x, we're looking at this function here. I think it's probably easier just to rewrite that as 3 times x to the negative second power. That derivative would be negative 6 over x to the third power. Now if we want to find dx dt, that's taking the derivative of this function with respect to t. And I keep giving you guys the same function. Sorry, we're not really practicing more of the trig functions here because we're doing sine one more time. But that derivative is just going to be the cosine of t. Now when we want to find dy dt, we can take dy dx and multiply that by dx dt. Okay. Now we need to make a substitution here though, because dy dx is in terms of x, right? Negative 6 over x cubed, and dx dt is in terms of t, cosine of t. So if we want to find dy dt, that means everything needs to be in terms of t. We're going to make a substitution here and call that negative 6 over, remember x is sine of t, so sine cubed of t, and then multiply that by the cosine of t. Now you should actually simplify this a little bit further. In the back of your book, they usually simplify all these trig functions here. So I'm going to rewrite this as the cosine of t over the sine of t, and then multiply that by 1 over sine squared t. So we have negative 6 times the cotangent of t multiplied by 1 over sine squared, which is going to be cosecant squared t. So this is the derivative of x with respect to t. I'm sorry, the derivative of y, my bad, with respect to t. All right, in our very last example, we are given two separate functions. A is equal to pi r squared, and r is equal to 3t plus 1. We are supposed to find the derivative of a with respect to t. However, a is not in terms of t. So we can approach this two different ways. We can rewrite a in terms of t by making a substitution right away, and we can write r as 3t plus 1 squared. So now a is in terms of t, and we can go ahead and just differentiate a with respect to t, just like we normally would with a composite function. So our second option would be to find this derivative of a with respect to t by first finding the derivative of a with respect to r and then multiplying that by the derivative of r with respect to t. Now this would be really similar to example 6. We would have to make sure then that we would substitute r equaling 3t plus 1, so everything would be in terms of t. And since we just worked on that in the previous example, I'm not going to use this strategy. We're just going to work on finding the derivative of a after you've already made the substitution. So we're looking at a composite function, and in this particular case, this is a squared function primarily, right? This pi out in front is just a constant, so when we find the derivative here, first we're going to take that 2 and multiply it by pi, so we have 2 pi times the inside function raised to the first power. Then, using the chain rule here, we have to multiply by the derivative of that inside function, so that's just going to be 3. So if we simplify here, we have 6 pi times 3t plus 1. So this is the derivative of a with respect to t. Now in part B, it says that given r is in centimeters and t is in seconds, what does the derivative of a with respect to t represent? So if you go back to the original equations here, I didn't mention this right away, but obviously a equaling pi r squared, that's simply the area of a circle, and r equaling 3t plus 1, this is the radius with respect to time. So as time increases, the radius will increase. So dA dt represents a rate of change, okay? This is always going to be a rate of change. So in this case, it represents the rate at which the area of the circle is changing. Circle is changing with respect to the change in time. Now in this particular case, since the radius is in centimeters and t is in seconds, then the area is going to be given by centimeters squared. So it's in terms of, centimeters squared per unit of time. So this would be the units on that particular derivative. All right, and that's the end of our lesson for today. So make sure tomorrow you're comfortable with using the chain rule, and you can use it and be a pro at any problem that involves using the chain rule, because in our next lesson you'll need that skill when we work on implicit differentiation. All right, nice job. I will see you guys in class tomorrow.